Black holes are among the most bewildering truths the universe has to offer. To call them objects is almost misleading. A black hole is less a thing you can point to and more a consequence. An extreme warping of space-time itself, so severe that the normal rules of intuition begin to crack. Around that distortion, reality starts behaving in ways that feel like science fiction. Light can be trapped, time can slow to a crawl, and the very geometry of the cosmos can fold into a shape that refuses to let anything go. Some of these effects sound so impossible that you might dismiss them outright. If we didn't have the mathematics to predict them with ruthless precision and an ever-growing mountain of observation showing that the math is not just elegant, it's right. I'm Alex Molan, and you're watching SRAM. In this video, we're going to reach toward the unreachable. We'll explore how black holes are born, what happens in their haunted neighborhoods, and what, if anything, could help something escape from the most unbreakable prisons the universe can build. And if you enjoy the journey, I hope you'll like the video and subscribe before we're done. Black holes come in a staggering range of sizes. The smallest confirmed ones are only a few times the mass of our sun, around 3.8 solar masses for one of the lightest observed candidates. But at the other end of the scale, we find monsters, black holes that grew in the early universe and now weigh billions of solar masses. Some are so vast that if you replaced our sun with one, the diameter of its event horizon could swallow the entire solar system with room to spare. The black holes forming today usually begin as the final chapter in the life of an unusually massive star. And for most of that star's life, it survives by balancing on a knife's edge between two forces. The first force is gravity, forever pulling the star's mass inward, trying to crush it down toward the center. The second force is outward pressure created by nuclear fusion. Deep inside the star, hydrogen nuclei slam together with such ferocity that they fuse into helium. In that fusion, a small amount of mass becomes energy, released as heat and light, and that radiation pushes outward, resisting gravity's squeeze. For millions or billions of years, the star hangs in this delicate truce, gravity pressing in, fusion pushing back. But stars do not get infinite fuel. When hydrogen runs low, the balance begins to fail. If the star is massive enough, it doesn't simply fade. It starts fusing heavier and heavier elements, helium into carbon, then onward toward neon, oxygen, and silicon. Each step binds the star a little more time, until it reaches iron. Iron is the dead end of stellar fusion. Fusing iron doesn't give you extra energy to spend, it costs energy. So once iron starts accumulating in the core, the star loses the very engine that was holding gravity at bay. The core grows heavier, denser, more helpless, until gravity finally wins, and it wins fast. The collapse is violent beyond comprehension. The outer layers of the star plunge inward like a cosmic hammer striking an anvil, crashing into the core with such force that the rebound becomes one of the largest explosions the universe can produce, a supernova. In that explosion, as matter and energy are flung across space, and the blast forges elements heavier than iron, up to gold, platinum, and even uranium, seeding the cosmos with the raw ingredients for planets, chemistry, and life. What remains after the explosion depends on the star's original mass. If the collapsing core isn't heavy enough, it becomes a neutron star, a sphere only a few dozen kilometers across, roughly up to approximately 25 kilometers in diameter. but packed so densely that a single teaspoon of it would outweigh mountains. Its matter crushed into an almost unthinkable state. But if the core is massive enough, then the story becomes stranger. Neutron pressure fails, known physics strains, and the collapse continues until what's left is a black hole. Now, here's the twist. When you see an image of a black hole, the dark ball you're looking at is not the black hole itself. Scientists suspect the true core, whatever it is, may be far smaller than even a neutron star, potentially compressed into something like an infinitely dense point, a singularity, where our current models stop giving clear answers. We can't see it, we can't directly measure it, and we may never be able to for one simple reason: the event horizon. Long before black holes were observed, we understood gravity in the Newtonian sense. Mass attracts mass. But in 1915, Albert Einstein reframed gravity as geometry. In general relativity, mass doesn't merely pull on things, it curves space-time, and objects move along that curved shape. Soon after, Carl Schwarzschild worked out a solution to Einstein's equations showing something astonishing. If an object becomes dense enough, the space-time can curve so steeply that there exists a boundary beyond which escape is impossible, not just for rockets, not just for atoms, not even for light. And if light can't escape, if even massless photons cannot climb out, then nothing can. That boundary is the event horizon, the point where gravity becomes so absolute that every path forward leads deeper in. When you see a black hole, you are really seeing the silhouette of this boundary, outlined by glowing matter around it, and by the way it bends and devours light. But black holes don't only distort space, they also distort something even more intimate: time. Einstein's picture of the universe ties space and time together into a single fabric, space-time. And when space-time is intensely curved, time behaves differently depending on where you stand. To an observer far away, something falling toward a black hole appears to slow down. As it approaches the event horizon, its motion seems to stretch, as if the universe itself is reluctant to let it cross. Right at the edge, it appears to freeze, hovering forever, never quite disappearing in a clean, dramatic swallow. Instead, it fades, growing dimmer and redder until it slips beyond detection. It looks like time is stopping, and in a sense, for the outside observer, the horizon marks a place where the story can no longer be watched. For a long time, black holes were treated as mathematical ghosts, beautiful solutions that might not exist in nature. But in 1964, evidence arrived. Early X-ray satellites detected an intense source of X-rays in the constellation Cygnus, something bright and high-energy radiation, yet strangely invisible in ordinary light. If it were a normal star, it should have been shining in visible wavelengths too. That object became known as Cygnus X1. By 1970, better observation showed that whatever Cygnus X1 was, it was locked in a binary orbit with a visible companion star. From the companion's motion, scientists could estimate the invisible object's mass around 15 times the mass of the Sun. That was far above the theoretical upper limit for neutron stars, roughly a few solar masses. The conclusion became difficult to avoid. This was likely the first strong black hole candidate ever identified. Since then, black holes have gone from rumor to population. We've detected them through their gravitational influence, through X-ray emissions from their surroundings, and even through images of their shadows against glowing disks of infallen matter, accretion disks heated to millions of degrees by friction and turbulence. A black hole with no infalling matter is, for all practical purposes, invisible. No bright disk, no fireworks, just a silent curvature in the dark. And yet the story gets even stranger. You might wonder, do black holes only grow forever? Will they keep feeding until the universe is empty? In 1974, physicist Stephen Hawking proposed something that sounded almost heretical. Black holes might not be eternal. They might slowly lose energy and therefore mass over time, because energy and mass are interchangeable, as expressed by Einstein's famous relationship E equals mc squared. Leaking energy means shrinking. But how could anything escape an event horizon? To understand Hawking's idea, as we have to step into the dreamlike logic of quantum mechanics. And before we do, let me ask you something that sounds simple, but isn't. What is nothing? Imagine a region of space completely empty. No atoms, no dust, no radiation passing through. It looks like perfect nothingness. But is it truly empty? Here's the clue. Light can travel through that nothing, and light behaves like a wave, an electromagnetic ripple. But a wave is usually a ripple in something. Ocean waves move through water. Sound waves move through air. So what exactly is waving in the vacuum? Modern physics answers with a startling idea. Even empty space is filled with fields, quantum fields, spread throughout the universe. Not particles floating in a void, but underlying fabrics that can vibrate. And when those vibrations rise above a threshold, the universe registers them as particles, electrons, quarks, photons, matter and energy, as notes played on invisible strings. In that view, the cosmos isn't a collection of objects so much as a symphony of fields. And quantum mechanics adds one more unsettling rule. Due to the Heisenberg uncertainty principle, those fields cannot be perfectly still. Even in empty space, they fluctuate. Briefly, pairs of particles and antiparticles can appear and vanish, so-called virtual particles, so long as they annihilate quickly enough to obey the universe's accounting rules. This isn't just philosophy. The Casimir effect, demonstrated by Hendrik Casimir, shows measurable consequences of vacuum fluctuations. Place two conductive plates extremely close together, and the allowed fluctuations between them change. The pressure differs inside versus outside, and the plates are pushed together. An eerie, physical fingerprint of the vacuum's restless activity. And this is where the black hole returns to the story. Because if the vacuum itself seethes with fleeting particles at the edge of a black hole, then Hawking realized something profound might happen. Something that could make a black hole leak energy slowly at first, and then faster and faster as it shrinks, until its final moments end in a dramatic release. If that's true, then the universe is even stranger than it looks. And we're only getting started. In theory, the pressure is higher outside the plates, because more virtual particles are allowed to flicker into existence there. That greater vacuum pressure gently but relentlessly pushes the plates toward each other. In the lab, it really happens. The plates move. The void reveals a grip. At first, that sounds like a violation. Matter appearing out of nothing, as if conservation laws were being mocked. And you'd be right to feel uneasy. Physics doesn't let you get something for free. So the universe keeps its books balanced in a way that feels almost poetic. When a particle appears, a second one appears with it, a matched pair. One is matter, the other antimatter. One counted as +1, the other as -1. So the total remains 0. The cosmic ledger stays clean. Most of the time, these pairs don't last. They collide almost immediately and annihilate each other, erasing themselves before they can become real in any everyday sense, which is precisely why most of space remains, for all practical purposes, empty. It isn't empty because nothing happens there. It's empty because what happens there cancels itself out faster than you can blink. There's even a mind-bending interpretation that antimatter might be matter moving backward through time. But that's a deeper rabbit hole than we need right now. The crucial point is simpler and stranger. Quantum fields are always trembling, always trying to sing, always silencing themselves again. Now ask the dangerous question. What if you could interrupt that cancellation? What if you could press your thumb against the universe's guitar string and mute just part of the melody? That is where black holes enter, not as simple vacuum cleaners in space, but as profound distortions that change the rules for what can cancel and what cannot. Their event horizons act like a boundary condition on reality itself. Inside, our space-time is bent in a way that cuts off information from the outside world. And when you impose a boundary like that on quantum fields, you don't just hide things. You reshape the kinds of fluctuations that are allowed to exist. Hawking imagined tracing a line through time in a region of space where a black hole forms, a timeline that runs from before the horizon into the future where the horizon exists. Before the black hole is born, the quantum fields fluctuate freely. Pairs appear, pairs annihilate. The universe stays, on average, calm. But once the event horizon forms, the geometry changes outside it and, crucially, across it. The event horizon doesn't need to emit anything like a star. It simply forces a mismatch. Hawking realized that after the horizon appears, some of the field's fluctuations no longer have partners that cleanly cancel them out in the same way. In the math, something survives, and what survives, when you look from far away, has the signature of thermal radiation drifting out into space. Radiation is energy. Energy doesn't come from nowhere. If something radiates, something pays. So Hawking's conclusion was as terrifying as it was elegant. If black holes produce this radiation, then the mass energy of the black hole must be decreasing to cover the cost. Over unimaginable spans of time, the black hole would shrink. And as it shrinks, the process accelerates until the final moments become a kind of last flash, an ending that is not silent, but bright. Hawking radiation is like finding money materializing on the sidewalk outside a bank, while the vault inside is losing the exact same amount. The outside gains, the inside pays. The universe never breaks conservation. It just hides the bookkeeping in geometry. The problem is that Hawking also predicted this radiation would be absurdly faint for astrophysical black holes. For many of them, it would be colder than the cosmic microwave background that already floods the universe. Its wavelength would be enormous, comparable to the size of the event horizon itself. If the horizon is solar system sized, the radiation is stretched to matching scales. That's the kind of signal that gets drowned in the universe's existing noise. In other words, we might only be able to see it clearly in a far future cosmos, colder, darker, quieter, when everything else has faded, which is a bleak punchline, because a universe that quiet may not contain observers like us anymore. And yet, despite the difficulty, scientists have tried to corner the idea experimentally, not by measuring a real black hole, but by building an analog. A clever approach came from researchers who created something like an acoustic black hole, a setup where a flowing medium moves faster than the speed of sound within it. In that region, sound waves trying to travel against the flow can't escape because the current outruns them. It's an event horizon, but for phonons instead of photons. Sound is slower than light, so this kind of horizon is far more achievable in a laboratory. The eerie part is that Hawking's mathematics doesn't care whether the horizon traps light or sound. It cares about the presence of a horizon, about the boundary and the way it slices the field's allowed fluctuations. In these analog systems, researchers observed emissions consistent with Hawking-like radiation. After tens of thousands of repeated measurements over long runs, they found patterns that matched the thermal predictions Hawking's framework suggests. It doesn't prove, beyond all doubt, that astrophysical black holes evaporate exactly this way, but it is strong evidence that the underlying mechanism Hawking identified is not fantasy. The horizon really can coax radiation out of the vacuum and force the price to be paid somewhere else. So, if you fall into a black hole, can you escape? Probably not in any meaningful, intact sense. But if Hawking is right, then over the long, dying twilight of the universe, the black hole will continue shedding energy until, eventually, everything it ever swallowed is not simply trapped forever. It is erased, converted, bled out into radiation bit by bit until the black hole itself is gone. Would that count as escape? Not the kind you'd want, not the kind that leaves a survivor, so yes, best not to go in. And black holes aren't done being weird, because Hawking radiation hints at something even more unsettling. It suggests reality may not work the way our instincts insist it must. Think of a footprint on a beach. You never doubt the cause. Your foot makes the print. The print does not make your foot. Causality feels obvious. So obvious that questioning it feels silly. But cosmology has a habit of turning obvious into fragile. Galileo's relativity taught us something disorienting. From inside a sealed room, constant motion and rest are indistinguishable. Drop a ball in a smoothly moving ship and it falls straight down in your frame, even though someone watching from shore sees it trace a diagonal. Without an external reference, both descriptions are valid. Motion is not absolute. It's relational. Einstein sharpened that lesson into something more profound with the equivalence principle. In a sealed room, the sensation of gravity is indistinguishable from acceleration. If your windowless capsule in deep space accelerates upward at 1 g, you will feel weight, just like you do on Earth. The universe gives you no internal experiment to prove whether a force is pulling you down or the floor is accelerating up to meet you, and that leads to the deeper picture. Gravity is not a pulling force in the usual sense. It is the experience of moving through curved spacetime. You want to travel straight. Spacetime says the straightest available path bends, and that bending is what you call gravity. As John Wheeler famously summarized it, spacetime tells matter how to move. Matter tells spacetime how to curve. So far, nothing is too offensive to common sense. Big masses make deep curves steer motion. But Hawking radiation adds a strange reversal. because Hawking's effect is, in a crucial sense, non-local. It doesn't come from the singularity. It doesn't even need to be produced right at the razor edge of the event horizon in the cartoon picture where one particle falls in and the other escapes. The region relevant to the effect can extend far beyond the horizon, enormous distances where, to our intuition, there is nothing at all. And yet the curvature imposed by the black hole changes what the vacuum is allowed to do in that whole neighborhood. Here's the unsettling chain. If energy leaks away from the curved space-time around the black hole, then the curvature must lessen because energy is conserved, and if curvature lessens, the black hole shrinks, which feels backwards, like saying the footprint shrinks, and therefore the foot shrinks with it. It's deeply counterintuitive, as we are comfortable with mass causes curvature. We are less comfortable with changing curvature changes mass. But Einstein's equations say curvature and energy are linked, tied together, without necessarily declaring a one-way arrow of causation the way our everyday minds demand. And that opens a speculative but haunting thought. What if mass is not the hand and curvature the shadow? What if, in some sense, mass is the shadow and appearance projected by something more fundamental in space-time itself? When you shine light past your hand, the shadow on the wall isn't a separate object. It's a projection created by geometry, by obstruction, by relationships. We assume we are the hand, and space-time is the wall. We assume our mass is the real thing, and curvature is what we imprint onto the universe. But do we know the arrow can't point the other way? Could we be the projection? Patterns that appear because space-time is curved a certain way, while believing we are the source? Relativity warns us, if two scenarios cannot be distinguished by any experiment available inside the system, you can't casually declare one real and the other impossible. Sometimes the universe allows multiple descriptions of the same truth, each one complete within its frame. To be clear, this is still in the realm of interpretation and philosophical consequence. Hawking radiation itself remains extraordinarily difficult to confirm directly for real black holes, even if analog experiments strengthen the case for the mechanism. But the point is not whether this thought changes your morning routine. You will still think, feel, choose, love, grieve, hope, and that lived reality is real enough to matter. The point is what black holes do to the mind. They force us to admit that our most basic assumptions about space, time, cause, and even what counts as real may be local habits, not universal laws. And that's why black holes are not merely destroyers. Yes, they swallow. Yes, they erase. Yes, they look like endpoints. But what if they are also doorways, tools the universe accidentally built, hints toward physics that could one day explain faster than light shortcuts, or new ways to handle energy, not by breaking laws but by exploiting the structure beneath them? To go further, we need to talk about the only three properties we can state about black holes with high confidence, because the horizon hides everything else. They have mass, they can have electric charge, and they can have angular momentum, spin. And once you understand what those three numbers really mean, the next chapter gets even stranger. You might wonder how we can claim to know anything about a black hole at all, when no light can climb back out to bring us news from inside. The answer is that the few things we do know are precisely the things a black hole cannot hide. They are not details of its interior. They are fingerprints in the space outside the event horizon, properties that leak into the universe through gravity and fields, the way a scent leaks under a door, even when the room is sealed. Those three fingerprints are mass, electric charge, and spin. Start with charge. If a black hole carries electric charge, it behaves outside the horizon exactly like any other charged object. It attracts opposite charges, repels like charges, shaping the motion of charged particles nearby. Imagine it as a cosmic magnet for electricity, quietly rearranging the dance steps of matter around it. By watching how known charged objects accelerate, curve, and fall, scientists can infer what kind of electric influence must be present, whether the black hole is electrically neutral or whether it's carrying a net charge of its own. Then there is mass, the big one. Mass is the reason the event horizon exists in the first place. It's mass that carves the deep gravitational well and bends space-time into a slope so steep that escape paths disappear. And because gravity acts outward through space, you don't need to see a black hole to measure it. You watch what it does to its neighbors. You measure the orbital speed of stars, the shape of their trajectories, how fast they whip around an invisible center. From those motions, you back calculate the mass that must be sitting there unseen. If charge is present, you account for that too. Otherwise, you'd confuse electrical attraction for gravity and get the wrong answer. Finally, spin, angular momentum. A black hole can rotate, and that rotation is not locked away inside the darkness. It drags space-time around with it like a spoon swirling honey. We'll get to how we detect that in a moment, but for now, accept the conclusion. Black holes are not just massive. Many of them are furiously rotating. Once you accept that, the scale becomes almost obscene. In theory, the smallest class sometimes discussed, micro black holes, could carry something like the mass of a moon inside a region thinner than a human hair. Think about that. A mass comparable to our moon, about 7.35 times 10 to the power of 22 kilograms, packed into a diameter measured in fractions of a millimeter. It's a density so extreme it stops sounding like matter and starts sounding like a glitch in reality. Then come the familiar stellar mass black holes, roughly 10 solar masses squeezed into a horizon only a few dozen kilometers across. Intermediate black holes might be 1,000 solar masses within a region still smaller than Earth. And above them all are the supermassive giants, hundreds of thousands to billions of solar masses, with event horizons that can span from a tiny fraction of an astronomical unit to hundreds of astronomical units, large enough to contain planetary systems like toys. And yet, here's the cold elegance of it. Beyond those three numbers, mass, charge, a spin, two black holes with the same values are indistinguishable. Put them in the same room, and if those three parameters match, no external measurement can tell you which is which. This idea is often summarized as the no-hair principle. Black holes are bald. They do not wear the story of what formed them on their surface. They keep their biography inside the locked vault, and they show the universe only the balance sheet. Still, those three numbers are enough to create effects that feel almost supernatural. Inside the event horizon, the usual notion of moving around breaks down. Space-time becomes a one-way geometry. But we suspect something lies at the center, some ultimate compression of mass energy that our equations describe as a singularity. In the simplest non-rotating models, it's a point. In rotating black holes, it resembles a ring, a loop of extreme density. That should already make you uncomfortable because spin is hard to define for something with no volume. And the discomfort gets worse. When you follow the math all the way down, certain idealized paths near the singularity seem to permit bizarre outcomes, loops in time, meetings with your own past, the kind of logic-breaking scenarios that spawn time travel paradoxes. The safest conclusion is not that time travel is casually available inside black holes. The safest conclusion is that our theories are incomplete. A true description of the core likely requires a successful marriage of quantum theory and general relativity, and we don't have that yet. The singularity may be less a real thing and more a signpost in the equations that says physics, as currently written, ends here. But whether the singularity exists exactly as imagined or not, black holes give us something we can talk about with more confidence, the region just outside the horizon, where the universe is still legible. And here, a crucial detail. The event horizon is not a wall you crash into. It's not locally obvious. If you fell toward it, your own clock would still tick. Your heartbeat wouldn't suddenly stutter because you crossed an invisible line. From your perspective, the fall can feel normal until you remember that normal no longer means what it used to. Because while your time keeps flowing, the outside universe can race ahead. In practice, the nearest sign of the horizon is something just beyond it, the photon sphere. There exists a razor-thin region where light itself can orbit. A photon, entering at precisely the right angle, can circle the black hole the way the moon circles Earth. It's unstable, delicate, and lethal. Given the sheer number of photons that have passed near black holes over millions of years, that region could be crowded with trapped, looping light. Pass through it, and you would be cooked by radiation long before you had time to be surprised. But beyond that, we reach the part we can use, the region where the black hole reveals its spin most dramatically. Because mass doesn't just bend space-time, a moving mass drags it. If you want an image for it, don't picture gravity as a rope pulling objects inward. Picture space-time as a flowing medium, and the black hole as a massive whirlpool that makes the medium rotate. In general relativity, this is called frame dragging. A rotating black hole twists the very coordinates of reality around it. Near enough to the black hole, you don't merely choose to orbit. Orbiting becomes compulsory. The stage itself is rotating under your feet, like standing on a moving walkway, except the walkway is space-time. As you get closer, the effect becomes overwhelming. In extreme cases, near the horizon, space-time can be dragged around so fast that, relative to a distant observer, it's as if the local frame is whipping along at speeds exceeding light. And your instinct screams, "That can't happen." Einstein forbids it. Here's the loophole, and it's a beautiful one. Einstein forbids objects from moving faster than light locally, within their own immediate frame. But space-time itself can expand, stretch, and move in ways that make distant frames separate faster than light without violating local physics. That's already familiar from cosmology. Galaxies can recede from us faster than light due to the expansion of space, even though neither galaxy is breaking the local speed limit. Near a spinning black hole, the same kind of logic applies. It isn't that you're sprinting past light in your local neighborhood. It's that the geometry you live inside is being dragged. And because frame dragging leaves observable signatures, twists in the motion of matter, precession of orbits, warping of accretion flows, scientists can estimate a black hole's spin by watching the swirl. Now comes the audacious idea. If space-time around a rotating black hole is a whirlpool, could you steal energy from it? Roger Penrose proposed exactly that. In the right region around a spinning black hole, where frame dragging dominates, you could, in theory, send an object in, split it, and have one part fall deeper while the other escapes with more energy than it started with. The extra energy is paid for by the black hole's rotation. You're not creating energy, you're siphoning it, mining angular momentum like a cosmic turbine. This concept is known as the Penrose process, and in principle, it can extract a substantial fraction of the energy tied up in the black hole's spin, on the order of tens of percent under ideal conditions. And that sounds like only a percentage until you remember what mass energy really means. Even a small fraction of mass converted to energy is apocalyptic in scale. E equals mc squared is not a formula, it's a warning label. Of course, the practical problems are inconvenient. You'd need a black hole close enough to reach. The nearest known candidates are thousands of light years away. A trajectory that survives tidal forces, and ideally a black hole without a blazing accretion disk. Because accretion disks are not gentle rings of dust, they are furnaces. Matter in them can reach millions of degrees, ripped into plasma, screaming out X-rays as it grinds around at relativistic speed. So yes, easy. But the significance isn't that we're going to build black hole engines next Tuesday. The significance is what this teaches us about faster-than-light dreams. You may never need to move yourself faster than light. You might instead manipulate space-time, the frame you're inside, so that the geometry does the impossible-looking motion for you, while you remain locally obedient to relativity. Frame dragging is not a fantasy. It's a real effect. And it's one of the places where black holes stop being merely cosmic graves and start looking like cosmic machinery. Now, here's another surprise you probably didn't expect. Falling into a black hole is often harder than your intuition says. We imagine black holes as ultimate vacuums. Gravity so strong that once you get anywhere near, you're doomed. And yes, if you cross the horizon, you're done. But for many black holes, especially the supermassive ones, matter doesn't simply drop straight in. Instead, it gets hung up in orbit. It forms a disk. It circles, heats, collides, and struggles. That disk can take enormous spans of time to be fully swallowed, sometimes millions, even billions of years, because the universe enforces a law that doesn't care how dramatic the situation feels. Angular momentum must be conserved. The same principle that makes a rocket push exhaust downward to go up is the principle that makes a spinning ballerina whirl faster when she pulls her arms in. When matter spirals toward a black hole, it almost never falls perfectly straight. It comes in with sideways motion. That sideways motion becomes angular momentum. And as the orbit shrinks, conservation demands the rotation speed increases faster and faster until it approaches the speed limit of the universe, the speed of light. And when matter hits that ceiling, it can't simply spin faster to keep falling inward. Instead, it piles up. It slams into neighboring streams. It grinds. It heats. It becomes friction made visible. That friction is why accretion disks glow. It's why they shine in X-rays. It's why the region around a black hole can be among the brightest things in the entire universe, even though the black hole itself is perfectly dark. The temperatures can climb to millions of Kelvin, hot enough to tear atoms apart into plasma. And in that violent churning, matter can radiate away a staggering amount of its mass energy, far more efficiently than nuclear fusion. Fusion in the sun converts about 0.7% of mass into energy. Accretion onto compact objects can release a much larger fraction, turning gravity itself into a power source. And that is the deeper point. Black holes don't just end stories. They rewrite the rules of how energy can be extracted from motion, from curvature, from the shape of space-time. And we're about to see just how far that rewriting goes. Pause on that for a second. The sun dazzles the solar system while converting only about 0.7% of its mass into energy through fusion. Now picture an accretion disk doing the same game with gravity, only far more efficiently. When a black hole's disk reaches peak brightness, it becomes a quasar, and a single quasar can outshine the combined light of every star in the Milky Way, sometimes by more than 1,000 times. The good news, if you can call it that, is that the disk doesn't just shed energy. It sheds angular momentum too. Fast-moving layers collide with slower layers above them, transferring momentum upward like a cosmic brake pad. The lower material slows, loses its grip on orbit, and finally begins to spiral down into the hole. And then come the most dramatic signatures of all, jets. We still don't fully understand why only some accreting black holes launch them, or exactly how they form. But the leading idea is that intense, twisting magnetic fields, wound up by the spinning disk and possibly the black hole itself, grab plasma and channel it into two narrow escape routes along the poles. Like a rifle barrel made of magnetism, they guide charged particles into tight beams and fire them outward at nearly the speed of light. These relativistic jets can stretch beyond their host galaxies, spanning millions, sometimes even billions of light years. And because their radiation is tightly focused, they can act like cosmic lighthouses. If the beam points toward us, we see it. If it points away, it can nearly vanish. One crucial detail: that power isn't coming from inside the black hole. Nothing escapes the horizon. The light and matter come from the disk, from the violent conversion of gravitational energy into heat, radiation, and motion, which leaves us with a strange truth. Black holes can swallow, yes, but under the right conditions, they also throw. They can hurl matter outward at relativistic speed, and the furnace-hot plasma around them can be as dangerous as their gravity. Getting close isn't automatically the same as getting in. So how big can black holes really get? To find the giants, you look to the centers of galaxies. The largest are supermassive black holes, grown over billions of years by feeding on gas, stars, and sometimes entire stellar systems. And here's the twist. Some of the most massive black holes we know appear in the early universe, are seen at enormous distances, meaning we observe them as they were when the cosmos was still young. A famous example is TON 618, estimated at about 66 billion solar masses, a mass comparable to an entire galaxy. We see it from roughly 10.8 billion light years away, which means we're looking deep into the past. Why would the young universe host such overgrown monsters? Part of the answer is selection bias. The farthest black holes we can easily detect are often quasars, because quasars are the brightest beacons in existence. This is related to the Malmquist bias. At extreme distances, we mainly see the brightest objects, while dimmer ones disappear beneath detection limits. So it may seem like the biggest black holes live far away, when in reality, we're simply blind to quieter giants closer in. Another part is cosmic history. Early on, the universe was denser, richer in gas, and more chaotic. Perfect conditions for feeding black holes fast. Over time, gas gets locked into stars, and many stars end their lives as compact remnants, removing material from easy recycling. With less free gas available today, the era of rampant quasar activity has largely faded. In short, the youngest and biggest pattern may be partly real, partly an artifact of what we're able to see. And as our instruments improve, especially as we map more black holes through their effects rather than their brightness, we'll get a clearer, less biased picture of how these monsters truly evolved. That's the unsettling beauty of black holes. They don't just bend space-time. They bend our assumptions about what the universe is willing to do.